Hi, everybody. So today is September 11th, Wednesday, and on Monday we started doing problem 297. So I've repeated our work that we did on Monday. So what we basically have is a rod that is supported by two cables, AB and AC. And there's also a load pulling downward on it, which is referred to as P. So what we did on Monday was we found the length of each vector. So we took the dimensions of each of those cables, knowing that the force has to be directed along those cables. Then we found the lengths of those two cables. Then finally, what we're working with is it says the resultant of P, AB, and AC is all directed along the rod. Well, the rod is on the x-axis, so that means that the x component will be equal to something non-zero possibly, but the other two, the J and K components, are zero, because in order to be directed along the x-axis, the y component has to be zero and the z component has to be equal to zero. Okay, so now we know a whole bunch of stuff, and what are we going to do with that? Well, the first thing we're going to do is, when we look at this resultant equation, what that means is if we take the component of P in the x direction and the component of AB in the x direction and the component of AB in the y direction, that's going to equal to the resultant, excuse me, that should say x, in the x direction. I gotta scoop it up a little bit. But it also means that if we take P in the y direction and add it to the component of AB in the y direction and AC in the y direction, that has to be equal to zero, as does those components in the z direction. That's the condition of this equation. All right, now we're going to start simplifying at this point. Now we got a whole bunch of general stuff, but now we're going to start simplifying. If we look at the force P, the force P is directed vertically downward. That means that P sub y has a component, but the component of P in the x direction is equal to zero, and the component of P in the z direction is also equal to zero. So we've simplified a little bit. The next part, and this is all new, it is on the numbered videos, but we're going to go through this. The question is, how do I find the vector force in AB and AC based on a tension, which is a magnitude, and a direction, which is along the cables? Okay, so that's going to be the question that we're going to answer today. All right, so the first thing is, if we are looking for any general force, we can say that is going to be equal to the component of the force in the x direction dotted with some kind of a unit vector. And a unit vector is generally called lambda. Now, what lambda means is a vector in a given direction with a magnitude of 1. So the reason that works is the vector F gets all of its magnitude from the component of the magnitude in some direction. Let's just get rid of that, times the direction with a magnitude of 1. So this multiplying anything by 1 does not change the magnitude. And because the component of a force is a scalar, not a vector, that means if we multiply it by vector, it gives it all the directions. So this accounts for the magnitude, this accounts for the direction, as long as it's equal to 1. All right, so let's take a look at the vector force AB. We know, I'm just going to give it a big F because I want to make sure to be clear. I'm talking about the force. We know that the magnitude of that was given to us in the book as being 183 pounds. But we do not know lambda AB. Lambda would be the unit vector along this cable, or in other words, the piece of the vector that has a magnitude of 1. Well, if you look at AB, it doesn't have a magnitude of 1, it has a magnitude of 61, doesn't it? So how would I find the component, the unit vector, along the AB with the direction of 1? Well, the thing is, you divide out the length. So we can write lambda AB then as being the x component, which is negative 48 over the length. And that's in the I direction. Then the j over the length. And the k over the length. And this is called the unit vector in the direction of AB. So that means that we can write force AB as being 183 pounds magnitude times negative 48 over 61I plus 29 over 61J plus 24 over 61K. Now, if you wanted to, you could convert these to decimals, but sometimes something will happen in the math that makes it a little bit easier. So I don't normally, I use it like this. The other thing that you'll maybe realize at this point, but it's kind of complicated, is that if you look at that first chunk, negative 48 over 61, negative 48 over 61, that's how far it extends in the x direction divided by the hypotenuse. So this number is actually the directional cosine with the x-axis. This is the directional cosine with the y-axis, and this is the directional cosine with the z-axis. That is very handy, and sometimes we can use it directly, but today I'm just making a note to show you how all of this trig works together. All right, so what that means is, if I did want to multiply everything through, I could write that force vector as being this times this in the x direction. So that would give me 183 times negative 48 divided by 61. I'll do it again. 183 times negative 48 divided by 61. And that is an even negative 144I. Similarly here, 183 times 29 divided by 61 gives me the component in the y direction. It's positive 85.6 J. And last but not least, we have 183 times 24 divided by 61 in the z direction, which is a full number 72K. And if you notice, this has units of pounds, this has no units, so the units on that vector is pounds. Did I misdivide? I meant to say 183. I did 183 times 29. Divide that number by 61. It's 87. Oh no, no, it's just me, just working from the seat of my pants instead of having it worked out ahead of time. All right, so now we have FAB. What is FAC? Well, in a similar fashion, it's TAC, that magnitude of the tension, times the unit vectors, the unit vector along vector AC. So if I look at that data, I have negative 48, 25, and negative 36, each one of those numbers divided over 65. But now I don't really know the magnitude of TAC, so I just have to leave it as a variable TAC. But I can write lambda AC as being negative 48 over 65I plus 25 over 65J minus 36 over 65 K. This is dimensionless. This is in pounds. So it's pounds. All right. I don't know the magnitude of KC, so I have to keep it as a variable, but I can distribute it through. And I get negative 48 TAC over 65I plus 25 TAC over 65J minus 36 TAC over 65K. And of course, that's still in pounds. Now I have two vectors. In order to do this equation, I need to find vector P. I can see it's totally negative in the vertical direction. So I could write vector P because it's going to be 0I. It's going to be minus the magnitude of P sub Y in the J direction plus 0 because it's all Y. Okay. All right. So just for ease, I'm going to need this piece of information and this piece of information. I'm also going to need my third vector P, which is just negative P sub Y J. All right, what am I going to do with those? Well, I'm going to solve. And here's what I need to know. I'm looking for R sub X. That's the resultant, right? That's going to be A sub BX or ABX plus ACX. But if I start with these other equations, something might pop out, which is what I'm going to hope for, right? So let's write out all three of those equations, filling in what we know, even though we're going to have to keep some of it in variable form. So my first equation, I'm going to write in the X direction, and I get simplified form A sub B in the X direction plus A sub C in the X direction equals R sub X. In the Y direction, I get P sub Y plus AB in the Y direction plus AC in the Y direction equals 0. And in the Z direction, I get A sub BZ plus A sub CZ equals 0. Right. So based on these equations, I have this data, and I can pick out, for example, the X components and take this and this, right? And those are going to be my two X components. Then the Y components, I have this, this, and this. And the J components, I have this and this, excuse me, this and nothing here. Okay, so I'm going to trust the math. Remember, if you have one equation, you can only have one unknown. But we have three equations, so we're going to be able to have three unknowns. How we're going to solve it, we don't know quite yet, but we're going to write in the numbers and trust, put our faith in the math. All right, what is A sub BX? Well, A sub BX is negative 144. That would be in pounds. What is A sub CX? Well, it's going to be negative. I have to write negative 48 TAC over 65, and that's going to equal R sub X. Right here, I have two unknowns, so I can't solve that equation directly. Two equations and one unknown, infinite number of solutions. Okay, for the second one, P sub Y, I know is a negative P sub Y, but that's all I know about it at this point. A sub BY is 87, and that direction is positive. And A sub C Y is positive 25 TAC over 65. Those three things added together equal 0. Again, I have two unknowns, so I can't solve this equation directly. But this looks kind of promising right here. A sub B in the Z direction is 72 pounds. And A sub C in the Z direction is negative 36 TAC over 65. Those two things added together equals 0. So I think I'm going to be able to solve for TAC immediately using the z direction equation. Okay, so the first thing I'll do is I'll take this term, the negative, add it to both sides. So I get 72 equals 36 TAC over 65. Then I'll multiply both sides by the reciprocal, which is 65 over 36. So on the left-hand side, I get 72 times 65 over 36. And on the right-hand side, I get 36 TAC. Oh, TAC cancels 65, so I just get TAC. All right. So now I have these numbers going to equal TAC, and I can solve for that directly. So the value is 72 times 65 divided by 36. And that value is 130, and we know the units to be pounds. All right. So if I go back to my original equation, I can then see that TAC is equal to 130 pounds. And anywhere that I have TAC in these equations, I can just substitute in 130 pounds and solve for the rest of it. All right. Now, the problem asks me the resultant determine the tension in cable AC. All right, I already got that, right? So good news, we got that. Now it says for the boom and loading in problem 297, determine the magnitude of the load at P. Well, we have to go back to those same equations again, don't we? Only this time we have one more number to plug in for a variable. So if I take a look at my y direction equation, I can say P sub y, which is what I'm looking for, plus AB in the y direction, which is 87, plus AC in the y direction, which is 25 times 130 over 65. Comparing it to my original equation, equals 0. So Py is equal to negative 87 minus this number 25 times 130 divided by 65, and that's 50. So if I do the math on that, I get Py is equal to negative 137 pounds. Okay. And there's the answer. So I would give you some advice, and I know I've said this on a number of lectures at all. Very important to stay organized and to do this like once in a while. You can cut to the chase and do a shortcut, but at this stage, I would not look for a shortcut. I would go through the math. And if you trust the math, you're going to come out with the answer, unless it's an invalid problem. But so what are my steps for a three-dimensional analysis? No matter what you're given and no matter what you're asking for, the first thing is to draw a free body diagram. The second thing is to write all forces, whether they're tensions, reactions, applied, whatever they are, in vector form. And when I say vector form, I mean IJK. The third thing is to find the length of applied forces. Here we found the length of AB and AC. And then write all unit vectors. So let's just do this as an example. That means that a vector force is equal to component force in X, I, plus component force Y, J, plus component force Z, K. Then the length is always going to be the square root of, hang on, or I need to put just a vector, let's call it length. This is probably what you're going to have. So the length then is going to be the length in the X direction squared, length in the Y direction squared, length in the Z direction squared, each term squared added together in the square root of that. Then you write all unit vectors. For example, lambda directed along vector L is going to be L sub X over L I plus L sub Y over LJ plus L sub Z over LK. All right. Then write the force vectors as the force vector is equal to a magnitude such as a tension times lambda along the vector. Next, write the governing equations. Generally speaking, it might be that the summation of forces in every vector direction is equal to 0. Or here, we knew that the resultant was equal to a resultant in the X direction. X direction times I, right? Or I guess here it was going to be, let me think, P, no, the resultant is going to equal the resultant in the Y direction times J. That's what we had on this case. Okay. Then set up the equations in each direction. And I would add, without looking for a shortcut, after you set them up, solve if you have one equation in one known, but the solution may be simultaneous equations. In other words, if you have two equations with two unknowns, you may have to set it up as 2 by 2 array, or if it's a 3 by 3, you may have to do a 3 by 3 array. But if you do these 8 steps, you will always be able to solve these kinds of problems. So do you think that these kind of solutions would lend themselves well to an algorithm in MATLAB? Yes, they would. Yes, they would. Yes, it's very exacting. It's a lot of bookkeeping. And so the other piece of that is when you do problems like this, especially on quizzes and exams, make sure that you show me all of your steps, because if you make an arithmetic mistake, or if you change the sign, or if you pick up a piece of X, or if you should pick up a piece of Y, I would like to give you a boatload of credit for that. I would like to give you a boatload of credit for the work that you did. All right. So make sure that you show me all of your work. And the other part is don't ever throw anything away. You know, like I walked into class today without my papers from last time. That is a terrible, terrible rookie move, because, you know, you never know when you're going to need them. But you guys were able to help me construct it. So that's it. It's good news. All right. I am going to quit recording, but I just want to mention I will be off campus Friday and Monday. So I'll be in this classroom again next Monday. But if you have any questions between now and then, I'll be in this classroom next Wednesday. Said it wrong. If you have any questions between now and then, do not hesitate to text me or email me, and I will get back to you as soon as I can. All right.